Hello, Math Studies students, and welcome to your online lesson. Today we'll be identifying key aspects of unknown functions, including intercepts, turning points, asymptotes, and domain and range. We'll know we're successful when we can use our technology to identify these key aspects of unknown functions. So unknown, we're talking about functions that we don't know that much about. So some functions that we have already explored in this class include linear functions, which we were just recently looking at in function notation. So, basically y equals mx plus b, or here you see it written as f of x equals ax plus b, where we have our slope and our y-intercept, and we know that the graph of which is going to be some sort of line. Then we know about quadratic functions. Their key element is having an x squared in there, and when we graph those, we end up with some sort of a parabola. And we know about things like that, such as vertex, axis of symmetry, maximums, minimums, things along those lines. So we want to take some of the knowledge that we already have and then apply this to a situation where we're given a function that we're not familiar with. Like, for example, instead of having a squared, what if it had a cubed or something like that? Well, how can we be expected to know anything about a function that we don't know anything about? Well, when dealing with unknown functions, meaning not linear or quadratic, we can use technology to help identify key features. And a major way in which we're going to do that is simply by graphing the function. The main functions that we are, or features that we are interested in, first and foremost, the axes intercepts. So where does our graph cross the x-axis and where does it cross the y-axis? We've done this for linear functions a little bit, and then we certainly spent a lot of time on this when we were talking about quadratic functions. And the technique that we'll use to find our x and y intercepts is almost identical to what we did for quadratics. And then another thing we're going to talk about is turning points. So what do we mean by turning points? Well, if I go back to the quadratic, a line doesn't have a turning point, but a quadratic does, because for a while it is going down. As we go from left to right, the graph is going down. And then for a while it's going up. Well, it turns right at its vertex right here. So basically when we talk about turning points, we're talking about vertices, and that's where we'll usually see our local maximum or local minimum. Now, why are we calling them local? Well, local, like if I have a couple turns like this, on that curve I have a maximum right here. But is it really the highest point that we ever get to? No, because all of this part of the graph right here is actually going higher. But for a while, it was the highest point. It was the highest point, anything immediately to the left or to the right. And then the same thing would be true for this minimum down here. It's a minimum compared to anything immediately to the right where it's going up, or anything to the left where it's also going up. But at that point, it's the lowest. However, later on, like in this region, as this graph continues downward, we will certainly not be the lowest overall point. So we call those local or relative maxima, which is just a plural for maximums. Domain and range, we've recently been talking about with regard to functions, so we'll be doing that. And then these last two we'll save mostly for our next video, but that'll be talking about where can x not occur and what asymptotes do we have, and sometimes those conversations sort of overlap. But for now, we're mostly just going to be talking about intercepts, turning points, domain, and range. We're going to do one example for the extent of this video. We'll spend a little bit of time on it. So given the function y equals 2x cubed minus 17x squared plus 42x minus 30, we want to create a sketch and find the intercepts, the turning points, the domain and range, and then the behavior as x. And then you'll notice there's this arrow here. And what we mean by that is it approaches infinity. So as x gets closer and closer to infinity, what is happening to our graph? And then as x approaches negative infinity, basically as our values go to the left, what is happening to our graph? All right, well, what we know so far, it's not quadratic because it has this cube there, or to the third power. Now, if I had gotten rid of that first term and just focused on this, it would totally be a quadratic. But because we have this extra little x cubed there, it's going to be a cubic, is what we call that. We don't need to know that. All we need to know is that it's a function that isn't one that we're familiar with. It's not a quadratic or a linear. So we are going to get out our graphing calculators and plug this function in. So I mentioned that we'll be using some skills that we already had. And one of those skills will be just graphing things in a calculator. So the first step to get any function, whether it's known or unknown in our calculator, is to go to the y equals. And then I'm simply going to type in my function 2, using my variable key x, to the third power I'm using the caret key for the third power. On some of the newer calculators, it will actually make it a high little exponent. Mine just writes caret 3 minus 17x squared. And you can either use the squared button or use the caret again. Plus 42x minus 30. All right, and now I'm going to graph this thing so I can actually see what it looks like. And if your window is not in its sort of normal 10 in every direction from the origin view, you can always press zoom and then 6, and it'll draw it back right here. Now, this is a pretty good view because I can see a lot of really important things right off the get-go. The first thing that we're supposed to do is look for intercepts, and I can see that I have an intercept here, here, and here. And all of these would be x-intercepts because they are crossing the x-axis. Now, the one thing I can't see is the y-intercept. And as this thing continues on, it would cross somewhere down there, but I can't see that happening. So we could address this a couple different ways. We could zoom out, but generally the way we find a y-intercept is not by using our calculator at all. The y-intercept occurs when x is 0. So to find the y-intercept, the easiest thing to do is simply plug in 0. And 0 is my favorite number to plug in. We'd be plugging in a 0 for this x, plugging in a 0 for that x, plugging in a 0 for that x, and there's no x with that last term, that negative 30. Well, 0 cubed is 0 times anything is 0, so this term is going to go away, this one goes away, this one goes away, leaving simply negative 30. So my y-intercept is 0, comma, negative 30. I plugged in a 0, got out a negative 30. Another way we can get that is if you go to second trace, or our calculate key, and just click the first one, which is value. And that allows us to put in an x value for this. And if I plug in a 0, which is what happens when we're at our y-intercept, and press enter, I see that it occurs when y is negative 30. Now I'm getting a little ahead of myself because I was supposed to sketch this graph. And I'm going to do a really sort of loose sketch here. We'll do 5, 10 in all directions. And I'm okay using this window of roughly 10 in each direction because that's what's on my calculator, and I can see the graph pretty well on that. Now, if I really wanted to get the y-intercept, I should probably go a little bit lower, and in fact, we know where the y-intercept's occurring. That's occurring at negative 30, which would be about here if I extend that down. And it's not a huge deal. We're just trying to get the basic shape, but I probably should have that on there. Now, as I look at this thing, it might be helpful actually to know my intercepts so I can plot those first before I make my sketch. So I'm going to go ahead and do that. Now, how do we find our x-intercepts? Well, x-intercepts we found when we were dealing with quadratics as well. That's any spot where the graph is crossing the x-axis. It's any spot where y is 0, sometimes referred to as our solutions or zeros or anything along those lines. Roots, I guess, is another one. So I press second trace, as always, and I go to my 0 option. Now, we can see here that we are going to cross the graph. The x-axis is going to be crossed by the graph 3 times. So we have to be very careful about where we are. You can see my little cursor up here. I'm going to focus on this first intercept right here. And to do that one, I have to be to the left of it. I hit enter. Now I'm going to go to the right of it, but not so far that I cross the next intercept, which is all the way over here. So right now I'm sort of at my max. I hit enter again. My guess, I hit enter. And I'm at roughly 1.27 if I round correctly. So 1.27 comma 0 would be my first x-intercept. I'm just sort of squeezing these answers on wherever I've got room. I'm going to do this again. Second trace. And I'm going to do 0 again. I will get rid of those little points. I'm going for the second one now, which is this one right here. And so I need to be a little bit to the left of it, which looks good. Hit enter. A little bit to the right of it. Hit enter. And then I make my guess. And so this one's a lot nicer. 2.5 would be my next x-intercept. So 2.5 comma 0. And then the last one, I'm going to do the exact same thing. This is the one furthest to the right, which would be this x-intercept over there. So I press second trace, 0. A little bit to the left, a little bit to the right, hit enter, and I have 4.73. So the last one, 4.73 comma 0. And these right here are my x-intercepts. All right, now we need turning points. I mean, I guess I could graph at this point. So we had one that was 1.27. I'll use a different color here. We'll do red. So halfway between the origin and 5 would be 2.5. I want about half of that. So that's going to be about here. And then I had another one that was right at 2.5, which would be about here. And then I had one at 4.73, which will be very close to 5. So we're basically looking at this, comes up, goes down, and then comes back up. Not my prettiest sketch, but it gives me a flavor of what's happening. I probably could have adjusted my window a little bit to just sort of focus more on that region and gotten rid of some of my negative x-axis, but that's the overall idea. All right, so now we're moving on to our turning points. So these would be our maximums and minimums. We can see that we have a maximum right here, and then we have a minimum right there. So let's go for those two values. Let's start with our maximum. So I'm going to press second trace, select choice 4, which is maximum, cursor to the left of my maximum, hit enter, cursor to the right of my maximum, but not going so far that I hit the minimum. And I have 1.82, comma, 2.19 approximately. All right, we'll do that again now for our minimum. So choice 3, I just want to be to the left of the minimum, be to the right of the minimum, hit enter, enter again, and this time for my minimum, I get 3.85 roughly, and then the y value would be negative 6.15. All right, so those would be my turning points. And again, it would be like right here was my max, which I've already labeled the coordinates off to the side, though we could certainly label these on our picture, and then our minimum right here. Next, we have domain and range. Well, relatively simple domain and range for both of these. For the domain, that's our left and right, and we can see that as this graph, I'm looking at the calculator here, continues on, it is going to the left and down, and then as we go to the right, it goes to the right and up. And so the domain x is given by from negative infinity all the way to positive infinity, because again, our lowest value, it's going forever to the left. Our highest value, it's going forever to the right. The range is pretty much the exact same thing. It's y, and we can see that over here, it's going down forever, and then eventually it goes up forever. So again, we're going from negative infinity to positive infinity. And then finally, the behavior as x is approaching infinity. So we're asking ourselves, what is happening as x is approaching infinity? And as x approaches infinity, what's happening to y? So let's look at this. Now, the graph, as we follow it, it starts off kind of down in the left, and then as it goes up, and then it comes down for a while, and then eventually goes up. But overall, as we continue from left to right, this graph, even though it had a little detour, is going to be going towards infinity. So as x gets infinitely large, y approaches infinity. Or you could say y gets bigger. That would be fine as well. And then in the reverse, oh, that was supposed to be as. So then as x approaches negative infinity, that means as we put in smaller and smaller values, that's as our graph goes to the left, what's happening to our y, and that y is going down. So y approaches negative infinity, or our y values are decreasing, going down. All right, so key things here. We had to actually put the function into our calculator in y equals in order to see it. We used second trace to find our intercepts, plugging in 0 to find our y, and then using the 0 function on the second trace, or the calculate function, to get our x-intercepts. We found the turning points by finding our maximum and minimum using second trace. Domain and range we used using our review skills from recently. And then we looked at the graph to see what was happening as x got larger and x got smaller. All right, that's it. Till next time.